C-Therm's purpose is to simplify thermal conductivity testing for the materials of tomorrow. Since 2007, we have emerged as the global leader in test instrumentation. Our core strength in thermal conductivity is built on now industry standard Trident instrument and broadened through strategic partnerships with Rigaku and Metrovid, providing one of the most dynamic portfolios in thermal and mechanical analysis.
Thermal conductivity describes a material's ability to transfer heat energy through conduction. In electronics, whether you're developing a smartphone, aircraft, or electric vehicle battery pack, the thermal conductivity of the materials is a major factor in the overall thermal management of the device. In other applications, like metal hydrides that are used as hydrogen storage media in fuel cells, the thermal conductivity impacts the kinetics of hydrogen adsorption.
The most common mistake we see in industry is applying a good method of measurement on the wrong type of sample. This is what happens when you're limited to a single tool and are facing a variety of sample formats. The Trident was designed to provide researchers with multiple options on a single instrument platform, so you always have the right tool for the job. It's been a huge success. Leaders like NASA, Adidas, Intel, Kimberly-Clark, Lucid Motors, and universities around the world choose C-Therm analysis tools and the support we provide.
C-Therm customers get access to the most advanced transient methods and are able to test under real-world application conditions, including humidity, temperature, or pressure. C-Therm's patented MTPS single-sided sensor is the fastest and easiest way to measure thermal conductivity. The Flex TPS is brilliant for more challenging applications and testing anisotropic and thin film samples. Our needle probe offers robustness for polymer melts. And the new THW is great for low viscosity fluids like engine coolants.
Not every client's ready to bring testing in-house, so we also offer industry-leading testing services here at Thermal Analysis Labs. C-Therm's highly skilled and experienced team provides access to the most advanced characterization tools for thermal properties and the expertise to make sense of the test results. For example, Rigaku's breakthrough sample observation capabilities allow users to video record a sample as it undergoes a heating cycle. When working with an unfamiliar material, you can see phase changes, crystallization, and other phenomena. This is vital for understanding the material and helping tell the story of how it behaves.
Metrovid's line of DMA offers the broadest frequency range and the highest force available on the market. This is just one of the reasons it is the standard in the rubber and tire industry. We work with a lot of folk developing different fillers for tires, including carbon black. And due to its sensitivity, the DMA is by far the best method to measure the glass transition point.
C-Therm aims to help accelerate material research and improve outcomes driven by better material performance data. Let us help you get the best possible data for your research. Simplifying thermal conductivity.
All right. Good day, folks. So we'll be getting started here in the next minute or so. Just a few housekeeping items I want to address before we jump into today's session. So the webinar today will be recorded and available for playback at the end of our time here today. So if for some reason you have to drop off early, or perhaps you know someone who you think might benefit from some of the content presented here today, there will be a link that you can open or share with folks after the webinar is over. I'll also make note of the Q&A feature in the webinar platform here. Somewhere, I believe, on the bottom right of the screen, there should be a little Q&A box. If you have any questions throughout today's session, we won't be doing anything live, but you can post your questions there, and we will be reviewing those together at the end of the webinar. So stick around for the final few minutes if you are interested, and we'll go into some of those questions together. Okay, so that being said, about a minute past the hour, so I think we can go ahead and get started here. So I'll get going. So welcome to today's webinar. My name is Arya Hakimian. I'm an applications scientist here at C-Therm Technologies. And today we're taking a look at really exploring the thermal conductivity of aerogel materials. So this will be the main focus for us here today. Now, going into today's session, I'll start with just a bit of a quick background on C-Therm, who we are, what we do, for those that may be unfamiliar. So C-Therm Technologies, we are really experts in the measurement of thermal conductivity, specifically in the transient class of measurement technique. So this is what we'll be focusing on, of course, here today, transient methods for thermal conductivity testing. Really, our goal through the development of these methods is really to simplify thermal conductivity testing for the materials of tomorrow. So, as we go through to today's session, this will heavily feature the Trident platform, and really specifically here today, the MTPS method, but we'll get to that. So we'll just quickly introduce Trident. So this is our flagship instrument. Trident in itself is a modular device. So it brings together 4 prominent methods for thermal conductivity testing. Really the idea here with the different methods is, testing a solid versus a liquid, something low versus high conductivity. The different testing conditions of interest. These can all really dictate which method is most appropriate, and we'll see that they can have different uses at different times. So this is Trident, and of course this is our thermal conductivity instrument. But I will also just highlight that we are partnered with both Rigaku and Metrovib for their line of thermal analysis and dynamic mechanical analysis testing instrumentation in North America. So if you have interests outside of thermal conductivity, maybe related to DSC, STA, or DMA testing, certainly happy to address those questions and support those endeavors as well. Lastly, I'll make note of our contract testing division, which is Thermal Analysis Labs, or TAL. So, for folks that maybe aren't looking to do testing in-house, whether that's related to availability, budget, whatever that may be, but you do need testing services, we can also happily provide those. So Thermal Analysis Labs has a full range of solutions, all of the methods and the instrumentation that we offer through capital equipment purchase side of the business is also available as a testing option, as well as other methods that are prominent in the industry. So happy to have those discussions. All right. So, really the idea behind Trident is, the modularity. And this quote from Abraham Maslow really helps embody that. This is one we like to reference often, but when all you have is a hammer, everything looks like a nail. So this is related to the idea that depending on the situation that we're looking at, this can dictate which method can be most appropriate. Now, I will just say that within the realm of thermal conductivity testing, there are quite a few different options. One resource that we have that I would definitely recommend taking a look at if you haven't already done so, or maybe you're new to thermal conductivity, is our method selection guide. So this resource provides a lot of good background on all of the methods that we have available on Trident, as well as, again, other methods in industry ranging from transient to steady state, optical measurements, etc. So definitely a resource I would recommend checking out. Okay, and typically we like to end these intros with just a little client testimonial. Always like to hear what folks are saying about their experiences with us. This one here from American Aerogel Corporation, Robert Mendenhall, noted that this technology has allowed us to provide accurate quality assurance for our products that wasn't previously attainable by other methods. It has given us a competitive advantage. In fact, we've been awarded contracts partially due to the superiority of the instrument over every other means of quality testing. So really nice testimonial there. If you want to check out what other folks have said about their experiences with us, you can check that out online. Excuse me. Okay, so aerogels, what are they? So, wanted to do a quick little background here. Aerogels are well known to be very lightweight, highly porous solids containing high volumes of air. This results in a very low density and thermal conductivity. Excuse me, one second. Okay, sorry about that, folks. So with these materials, one of the really interesting aspects is that their unique structure. These pores really allow a very unique aspect, and it's where it gets its actually visual look from, called frozen smoke. Now, over the years, aerogels aren't, I would say, inherently new. They've been around for a while. Since the 1930s, when they were initially developed, used on various methods, various different missions, through NASA and other researchers. And more recently, and something that we'll focus on in today's session, is actually some of the more novel use cases of more polymer and bio-based aerogels and how those performances compare to the traditional silica counterparts. So that being said, we're going to really break these down into a few different types of aerogels. Your traditional silica options, these have among some of the lowest thermal conductivity values. This is the classic fragile, frozen smoke looking aerogel material. There are also a variety of polymer-based aerogels. These have, as we can see, slightly higher K, but noted to be very flexible, much stronger in their mechanical properties. And then bio-based options. So, with the advent of, the green tech and trying to move to more renewable resources, bio-based composites are, popping up everywhere, as well here showing in the aerogel space. So we'll take a look at a few different examples of how these materials perform, some of the different considerations around their performance and the testing setups required. Now, this all brings us to thermal conductivity, right? So what is thermal conductivity? Again, this may be a review or something that this is very well known for folks, but again, to folks that are maybe newer to the topic, thermal conductivity effectively describes a material's ability to transfer or conduct heat energy. This is an intrinsic material property, meaning it is independent of the size or the shape of the material. And just as a note, for all content presented here today, we'll be referring to the standard units in watts per meter Kelvin. So, thermal conductivity, and this is really the performance metric of these materials, but why are aerogels so insulative? So having very low thermal conductivity. Again, as mentioned at the beginning there, this is it's related to the combination of the fact that they have these very unique nanoscale pores filled with this gaseous content, and essentially it is reducing the effective heat transfer paths within the sample. So, when we're looking at, some of the transfer here, these air molecules are going to collide more with the pore walls than they will each other. So you get less of this carrying of energy across those different barriers. So essentially the heat has to, view as like hopping across many of these gas-filled pores, which is quite frankly, a very non-efficient way of moving heat around. So what they're really good at is, of course, reducing that heat transfer. And actually, there's a unique, excuse me, a unique property here, the Knudsen effect, which is related to the fact that when that air or that gas present in those voids is condensed and extremely small, you actually end up having a net decrease in thermal performance compared to that even of just pure air, which is somewhere around 0.02 watts per meter Kelvin. So you can see that the aerogel actually has a solid mass to it, but resulting in a lower thermal conductivity than air alone. And, to compare that to the classic opposite end example of this, copper having a thermal conductivity of 400 watts per meter Kelvin. So we can see the order of magnitude differences here in the range of performance from something very insulative to something quite conductive. All right. Now, when it comes to talking about actually measuring and quantifying performance here, there are a lot of options that exist, as I've mentioned, but some of the more traditional methods, so your steady state guarded heat flow meter, things of this sort, have their challenges. One of the main aspects is the relatively large sample size requirements that are typically needed for these steady state instruments. Oftentimes, especially in an R&D environment, producing some of these materials to this size is just simply not attainable. Now, even if you are able to produce quite a large material, one of the other inherent drawbacks that can cause certain bottleneck, let's say, is the long test time. Steady state, your testing durations, we're looking at hours to days, depending on the method used. And this can be prolonged for the lower K materials. And of course, aerogels being some of the most insulative samples that are out there. And then lastly, your testing environment. So, excuse me, we'll be talking about some of the different aspects of the environmental considerations that can affect thermal conductivity. But we'll see how transient methods offer some unique testing setups to allow for some really interesting measurement. So this brings us to our transient methods, and specifically here, the MTPS. This is going to be one of the focus of today's session. The MTPS stands for the Modified Transient Plane Source technique. One of the things I'll flag here is that the sample size requirements for MTPS, it's about 18 millimeters in diameter. So again, we can get away with a much smaller sample piece here compared to the steady state methods. So some other notes of point here is it's a single-sided sensor. So one material is simply placed in contact. You can actually see an aerogel being tested on the image on the right there. There is a specialized aerogels calibration available with the MTPS, so inherently designed to handle these materials. Fast test times, and some of the variables of the environment that we can look at are things like humidity, temperature, and pressure, and we'll see some examples of that coming up. So wanted to start with just, a very basic, simple example, which is, room temperature measurements of some aerogels that were measured using MTPS. So these were some commercially available samples that were tested, all found to be within about 4% of the reference expected values. So, there's certainly quite a clear, I'd say fit here for some very basic testing. But this is, of course, just that, very basic, room temperature, setting up, doing some quick testing. But what can we look at that can maybe be of, let's say maybe more interesting here? So I wanted to talk about one of those environmental conditions, one of them being moisture. So moisture absorption is something that can be very detrimental to the insulative performance of the aerogel. This is because water, of course, has a much higher thermal conductivity than air. So if those pores start to fill with this liquid versus the air, you're going to essentially destroy that insulative performance of the material. Now, just as an example of this was some materials that we actually, they were sent to us. And when we did the initial testing of the aerogel, it tested quite high. Upon some further investigation, we found out that it was because this was actually shipped to us from a very humid climate and it was packaged in a box, but it still maintained that high humidity level. And when we opened it up for the initial testing, as we can see, once we let the sample dry out, and this was in an East Coast winter, so very dry conditions, we started to see a drop off in thermal conductivity. Tested it a week later, and now, okay, we see it behaving much more like what you would expect from a traditional aerogel. So your storage conditions and the testing environments can be very important. So something to keep in mind there. If you're producing or manufacturing these, sending these out to groups for testing, having that control around the moisture content is something to be aware of. Kind of following up on that, this is an example of a publication. It's one I like to show when we're talking about insulative materials in general. Now, it's not on a traditional aerogel, and it's actually just a bio-based kind of standard insulation, but it's a really nice data set here that I wanted to highlight. So this was some work out of Vietnam and France. And as we can see, again, just kind of moving on that idea of moisture content, some of these bio-based materials, insulations, again, increasing the relative humidity, you see a net increase in thermal conductivity, which in this context is something we are trying to avoid. We want it to have the lowest value possible. But what's interesting is as you cycle the condition of humidity over the testing, we can see how that trend starts to rebound and then repeat itself. So some materials are more, I would say, attuned to mitigating the impact of that saturation and also being able to come back to baseline, whereas others may be more, let's say, permanently damaged from that level of moisture contamination, let's say. This is a picture of the setup here. So again, with these transient methods, one of the really nice things is being able to set these up inside of a variety of different environments. The sensors kind of describe them as being essentially agnostic in that you can put them in different thermal chambers, humidity chambers, etc., and very easily test them under these different conditions. Okay, this next example here is actually a publication that came out this year. Is featuring some work done by NASA and the University Space Research Association on the impact of space environment exposure on polyamide aerogels. So what was really interesting in this paper is they were focusing on what happens to the material after it has been exposed to some condition. And in this case, very novel case, these materials, these aerogels, were actually placed on the exterior of the International Space Station, and then through multiple trips, then returned and tested, of course, tested before they left, and then tested after to see how the material properties changed from those exposed conditions. So we can see some of these images pre-flight, post-flight, and very similar in visual appearance. And actually, this is what they had really found out from their studies here. The impact of that exposure did not significantly have a negative influence on thermal conductivity. They also looked at the mechanical behaviors, and they found them to be well in line with what they were seeing pre-flight, which is a really interesting observation here, highlighting the really nice fit of this specific class of aerogel for those types of space exploration applications. Next up, I wanted to share an example of so this is an air-dried cellulose fibril foams prepared by a one-pot Pickering emulsion. Now, this was some work coming out that was really looking at a variety of different structural aspects of these materials. So, this is a, very similar low K insulative material. But the reason this is a really interesting study is what they were doing with the MTPS. Because the MTPS is single-sided, we can leverage its ability to measure, let's say, the top versus the bottom side of a material to get an understanding of that thermal conductivity at that relative location and understand behavior throughout the thickness. So because we're probing a few millimeters, if I have the sample in one side versus the other, and we see differences between those two results, as we're seeing in some of these here, of course, that can likely be attributed to some potential issues within the material itself. So for example, here, obviously the bottom side versus the top side, you can see that we're getting some large differences in just the densification and the overall structure versus some that were, we'll say, a little bit more uniform in nature. But that's the thing with the thermal conductivity measurement, is the value in and of itself is, of course, quite relevant for many applications. But how can we also leverage thermal conductivity as a proxy for things like this in terms of a quick QA/QC check, or as you're developing a variety of different formulations, ensuring the consistency not only across the sample, but throughout the thickness as well. And I wanted to end here with an example of, we talked primarily about aerogels and these insulative materials, but can you achieve aerogel-like performance, but just with standard insulations? Now, if we look back, I remember we showed that slide, the silica aerogels having, 13 milliwatts per meter Kelvin, some of the lowest. Some of the polymer and bio-based were a little bit higher here, but I wanted to show an example of just traditional basic polyurethane foam. So depending, of course, on the densification, the pore size, the structure, thermal conductivity range about 0.02 to 0.035 watts per meter Kelvin. This has application in a variety of different industries, from biomedical, transport, marine, space, packaging, etc. But what I would say we could maybe take a look at is some of those, again, representative conditions and how they can impact your performance, specifically testing under vacuum. So one of the things to keep in mind is that within these insulative materials, there's, of course, air voids or air entrapment. Now, closed versus open cell, there's, of course, differences there, but fundamentally, one of the things that we can modify here is that environment in which that sample is in. And specifically, with these transient techniques and the MTPS, we have a line of high pressure cells, which can be adapted to do testing under vacuum. So by removing the air from the system, we can actually lower the effective thermal conductivity as we're replacing that air with that void space. And this was a test that we ran here, and you can actually see under ambient conditions with the MTPS, it was about 0.028 watts per meter Kelvin on the polyurethane foam. But then when we actually subject it to vacuum, we see a significant drop. So this, really hitting into that, novel aerogels range, while, inherently not being a traditional aerogel in that sense. Excuse me. Now, of course, how and when would you apply vacuum? Obviously, it would depend highly contextual to the application space of interest. If you're never going to be able to subject this foam to vacuum in its use case, then this may not be as relevant. But for certain packaging systems, I know for some advanced, structural designs, vacuum is a part of that. So you could potentially leverage some of this in terms of maintaining a level of insulative performance. But overall here, this is really, I'd say, that the main takeaways from today's session, in that aerogels can achieve some of the lowest thermal conductivity values related to their unique structures. As we've shown, the transient class of measurements, especially the MTPS, can provide a means of testing very small format materials, and they're faster than the traditional steady state methods. Testing conditions, we showed a few different examples, but temperature, humidity, pressure, these can all have quite a significant impact on your thermal conductivity values. So, understanding which conditions are going to be relevant to your application and then being able to mimic those through your testing is really going to give you the best possible data for your research. So, if this type of content was of interest and you found that beneficial, we do have a list of previous webinars, again, that are available on our website. This one will be posted shortly for playback, as well as a variety of technical resources. We have a tech library that you can find access to a variety of the papers that we made reference to for this application, and of course, a lot of the other ones. So this is definitely quite a bit of content, so take a look there if that's at all of interest. I'll also take a moment to plug some upcoming webinars that we have scheduled. Later in the month, so the end of September, we'll be doing a thermal conductivity of polymer composites webinar. So somewhat similar to today's focus on aerogels, but for polymer composites. And then at the beginning of October 7th, we have a guest speaker, from MG Chemicals, coming in to talk about some of the testing and characterization of their thermal interface materials. So two ones coming up here over the next few weeks. I'll also just plug some of the events that we will be at if you happen to be attending these or in the area. Love to have a chat. Happy to stop by. We will be at NRW Nano Conference in Germany. That'll be September 30th to October 1st, as well as the Battery Show North America, which is going to be down in Detroit, Michigan, October 7th to 9th. If the testing aspect of this was of interest, but you maybe wanted to learn maybe a little bit more as it relates specifically to your application and your material testing needs, we happily scheduled these technical consultations, which would essentially give us, some time to go through, learn what you're looking to measure, and then provide some recommendations. We can show you a live demonstration of the instrument. These are very easy to book. We can get them done in 30 to 60 minutes. So if this is at all of interest, there's a link in the chat there. I'm happy to schedule one of those. But maybe if you like what you see and you're just looking for some budgetary information, you can also certainly request a free quote. With the modularity of Trident, depending if you just need 1, 2, 3, or all 4 sensor types, this will of course dictate some of the different cost structures. But, we're happy to provide some quotations there to give you access to potential end-of-year budgets or for scoping upcoming project needs. And as I mentioned at the beginning, Thermal Analysis Labs is our full service contract testing division. You can see some of the different testing options that we provide. Again, if testing services were something that you were looking for, these are, again, discussions we're certainly happy to have, provide a free quote for what that testing scope of work would look like. Again, whether it's thermal conductivity, thermal analysis, mechanical analysis, or otherwise, please feel free to reach out. And my last, I'd say, request is to give us a follow on LinkedIn. This is where we post all of our latest and greatest content, everything from upcoming webinars, blog posts, content pieces, conferences we'll be at, etc. So if you're not already doing so, give us a follow on LinkedIn. It'd be much appreciated. And that being said, this brings us to the end of the official webinar time. At this point, I would just like to thank the audience for your attention here today. If you're interested in sticking around for the Q&A, I'm going to go ahead and stop the recording here shortly, and then we'll pivot into that. I've seen a few questions come in already. So again, if you had any questions related to your samples, any of the content presented, please feel free to type that into the chat Q&A there. So for those of you that are dropping off at this point, once again, thank you for your attendance, and hopefully we'll see you at the next one.